So, last time we discussed the Volterra operator and we have proved using the Ascoli-Arzela theorem that the Volterra operator is a compact operator from L2 of 01 to L2 of 01. Now, we shall look at a more general class of operators known as the Hilbert-Schmidt operators. So, what are the Hilbert-Schmidt operators? Let us see, they are operators from L2 of 01 to L2 of 01. So, T from L2 of 01 to L2 of 01 given by Tf of x equal to integral 0 to 1 kxt f of t dt, where the kernel k of xt is assumed to be a continuous function on the square 01 cross 01. I would like to point out that the continuity of k is not really essential, but it makes life slightly easier, and for this particular discussion in this lecture series, continuity is enough. More generally, one can allow the k to be in L2 and that should suffice. So, anyway, so with this continuity assumption we shall proceed. Let us show that this operator Tf is a compact operator. Again, we are going to use the Ascoli-Arzela theorem. First, we shall establish that the family Tf, where f varies over the closed unit ball U, is actually equicontinuous, which basically means that this operator T maps L2 of 01 inside the space of continuous functions. Okay, so let epsilon greater than 0 be arbitrary. Then remember that k is a continuous function on the square 01 cross 01. The square 01 cross 01 is a compact metric space. A continuous function on a compact metric space is uniformly continuous. So, we invoke the uniform continuity of this kernel, and there is a delta greater than 0 such that mod x minus y less than delta implies mod k of x minus t minus k of y minus t less than epsilon. All right. So, now let us estimate mod Tfx minus Tfy, that is going to be less than or equal to, take the absolute value inside the integral 0 to 1 mod k of xt minus k of yt into mod ft dt. Now, I am going to assume that mod x minus y less than delta, in which case the factor mod k of xt minus k of yt is less than epsilon. So, the epsilon comes out and we are simply left with integral 0 to 1 mod ft dt. Again apply the Cauchy-Schwarz inequality and we get that this is going to be less than epsilon, because integral 0 to 1 mod ft dt is integral 0 to 1 times mod ft dt, and then by Cauchy-Schwarz inequality that will be less than or equal to the L2 norm of f, and L2 norm of f is less than 1. So, we have proved that mod Tfx minus Tfy is less than epsilon whenever mod x minus y less than delta. The delta does not depend upon f, the same delta works for all f varying over the ball U, and so this family Tf, where f varies over the unit ball, is an equicontinuous family. Now, we want to understand uniform boundedness. Okay, again we can estimate mod Tfx is less than or equal to, take the mod inside the integral 0 to 1 mod kxt into mod ft dt. Now, k is continuous on the square 01 cross 01. So, it is bounded. Let capital M be the bound M comes out of the integral. We get an estimate m times integral 0 to 1 mod ft dt, again less than or equal to m times norm of f is less than or equal to 1. So, mod Tfx is less than or equal to m, and this is true for all x in 0 1 and for all f varying over the family U, and so we get uniform boundedness. The Ascoli-Arzela theorem now tells you that the family Tf as f varies over the unit ball is pre-compact, and so the operator T is a compact operator as advertised. This is our second example of compact operators. Now, You will ask, why are we discussing this kind of functional analysis in such generality? We will now tie up this round of discussion with what we did in module 5. So, what was the theme of module 5? It was boundary value problems with 2-point boundary conditions. We looked at boundary value problems or the regular sturm Liouville problems on the closed interval 0, 1. So, we returned to this sturm Liouville problem, but with a functional analysis or a Hilbert space perspective. So, look at equation 7.10. We are looking at the differential equation y double prime plus lambda rho xy equal to f of x, where y of 0 equal to 0 and y of 1 equal to 0. So, now let us assume that lambda is not an eigenvalue of the boundary value problem with 0 right hand side. Namely, put f of x to be 0 and look at the boundary value problem 7.1 with Dirichlet boundary condition. Let us assume that lambda is not an eigenvalue. We will see why this hypothesis becomes relevant. Away from the eigenvalues, we are going to invert 7.10, and that is exactly going to tie up with the Hilbert-Schmidt operator. We are going to get a Hilbert-Schmidt operator as a result. Okay. So, first of all, let us look at the corresponding problem in linear algebra. Suppose you look at the problem of solving Ax equal to b, where A is a square matrix and B is a column vector. Now, if the homogeneous equation Ax equal to 0 has only the trivial solution, then we know that the inhomogeneous equation can either have no solution or a unique solution. That is, whenever we assume that the kernel of A is trivial, then we know that the inhomogeneous equation has at most one solution. That is why when lambda is not an eigenvalue, the equation y double prime plus lambda rho xy equal to 0 with Dirichlet boundary condition has only the trivial solution. That means that the kernel is actually trivial, and so the solution of 7.10, if it exists, it is going to be unique. Now, we shall show that the solution exists. We shall find an integral representation for the solution of 7.10, and that integral representation is going to turn out to be a Hilbert-Schmidt operator. It is going to be better than just a Hilbert-Schmidt operator. We will see that presently. So, when we solve 7.10, think of f of x, the right hand side, as a forcing function. The forcing function f of x should be thought of as the input function, and the solution of 7.10, which is unique and whose existence we are going to establish, will now give you a solution operator. That solution operator is going to be the operator t from L2 of 0, 1 to L2 of 0, 1. That is how we get this solution operator t. So, suppose y1x and y2x are solutions of the homogeneous equations. So, now how do we solve an inhomogeneous equation 7.10? To solve an inhomogeneous equation 7.10, we must take a basis of solutions of the homogeneous equation. So, let us take a basis of solutions. Let us take solutions y1x and y2x of the homogeneous equation y double prime plus lambda rho xy equal to 0, equation 7.11. Satisfying the condition y1 0 equal to 1, y1 prime 0 equal to 0, y2 0 equal to 0 and y2 prime 0 equal to 1. So, let us take these two solutions y1 and y2. What is the Wronskian of y1 and y2? At the origin, the Wronskian at the origin is 1. Look at the differential equation. The differential equation has no y prime term, so the Wronskian is constant. So, the Wronskian is everywhere 1, and the solutions y1x and y2x are linearly independent. So, we have got a complete solution of 7.11, which is a homogeneous equation. So, now how do we solve the inhomogeneous equation? To solve the inhomogeneous equation, we must appeal to the method of variation of parameters that I hope is familiar to you from the undergraduate courses. So, what is the method of variation of parameters? The particular solution of 7.10, the particular solution of 7.10 should be sought in the form yp of x equal to v1x y1x plus v2x y2 of x, equation 7.13, where the functions v1x and v2x satisfy the pair of equations v1 prime y1 plus v2 prime y2 equal to 0, v1 prime y1 prime plus v2 prime y2 prime equal to f. So, the last pair of equations for v1 prime and v2 prime have to be solved simultaneously, and we get v1 prime, we get v2 prime, we must integrate, get v1 and v2, and we get your particular integral yp of x 7.13. We have done numerous examples of this kind in undergraduate courses. For example, solving y double prime plus y equal to sin x, y double prime plus y equal to tan x. Hundreds of examples you have worked out in your undergraduate courses by the method of variation of parameters. So, here we shall put the method of variation of parameters to theoretical use. We are not solving a concrete specific numerical problem, we are rather developing a theory, but the method of variation of parameters is of extreme importance in obtaining integral representations for solutions. Okay, so when you solve these equations v1 prime y1 plus v2 prime y2 equal to 0, v1 prime y1 prime plus v2 prime y2 prime equal to f, what do we get? We get v1 prime individually and v2 prime individually, and we must integrate it. Integration means v1x equal to minus integral 0 to x y2t ft dt, and v2x is integral 0 to x y1t ft dt. So, we got the expressions for v1 and v2. We must substitute these expressions in the form of the particular integral. Remember, yp, the particular integral was v1 y1 plus v2 y2. So, when you put these expressions for v1 and v2, we get yp equal to integral 0 to x y1t y2x minus y1x y2t f of t dt, which can be written as integral 0 to 1 kxt f of t dt, where the kernel kxt is given by kxt equal to y1t y2x minus y1x y2t when t is less than or equal to x, and 0 when t is greater than or equal to x, because the original integral goes from 0 to x and I made it an integral from 0 to 1. So, when t exceeds x, we have to define it to be 0. So, this is the kernel, and observe that this kernel k of xt is continuous on the square 0 1 cross 0 1. Well, we have found a particular integral, but this is not going to work because we have not incorporated the boundary conditions. But remember that we have only obtained a particular solution. What is the general solution? Particular solution plus c1 y1x plus c2 y2x. To a particular solution, we must add the general solution or the complementary function, namely the general solution of the homogeneous equation. In other words, yp of x plus c1 y1x plus c2 y2x, the c1 and c2 have to be chosen in such a way that the boundary conditions are satisfied. We proceed to do that now. So, now our general solution is written over here in the slide, in the first display, and the constant c1 c2 have to be appropriately selected. So, let us put x equal to 0 directly. What is the boundary condition? Y of 0 equal to 0. So, the left hand side of the first displayed equation becomes 0. What about the integral term? Integral 0 to 0 k of xt f of t dt, that also drops out. Now, what are the conditions for y1 and y2? y1 0 equal to 0, remember, y1 0 equal to 1 and y2 0 equal to 0. So, what does that give you? It gives you straight away c1 equal to 0. So, c1 is also gone. Now, you put x equal to 1, again the left hand side is 0. So, you get 0 equal to c2 y2 of 1, c2 into y2 of 1 plus the integral term is integral 0 to 1 k of 1 t f of t dt. So, that gives you c2 equal to minus 1 upon y2 1 integral 0 to 1 k of 1 comma t f of t dt. So, we have got the C2 as an integral. Now, I have divided by y2 of 1. How can I be certain that y2 of 1 is non-zero? If y2 of 1 happens to be 0, this entire argument breaks down. But remember, what is y2 of 0? y2 of 0 is already 0. Now, if y2 of 1 also happens to be 0, then what will be y2? y2 will be an eigenfunction with eigenvalue lambda, because it satisfies the boundary condition and it is not the 0 solution. But remember, we have assumed that lambda is not an eigenvalue. I expressly said that lambda is not an eigenvalue. So, y2 of 1 cannot be 0, and so we have obtained an expression for C2 and it is valid. So, now let us put this value of C2 in the expression for y of x. C1 is 0, C1 is gone. We obtained an expression for C2 and we will get two terms both involving integrals, and we must combine these integrals into one integral. So, when you do that, to the algebra, you are going to get y of x equal to 1 upon y2 of 1 integral 0 to 1 k x t y2 of 1 minus k1 t y2 of x f of t dt. And the expression inside the integral has been written as integral 0 to 1 g x t f of t dt, where what is g of x t? K x t y2 of 1 minus k1 t y2 of x upon y2 of 1. Now, this g of x t is called the Green's function for the boundary value problem. The solution operator has been expressed as an integral of f. So, for each f in L2, we have obtained a unique solution for the boundary value problem, and that unique solution has been expressed as an integral, and this integral transform is the Hilbert Schmidt operator, because the kernel g of x t is a continuous function on the square, and we know it is a compact operator. Now, let us examine the Green's function g of x t in little more detail. You have to simply write out the expression in detail. We know k of x t for t less than or equal to x, and we know k of x t for t greater than or equal to x. We know this formula for k, and we have to put down this formula and write out the Green's function. Of course, it will have two different avatars. If t is less than or equal to x, then your Green's function will be y2 of 1. The constant y2 of 1 I have clubbed with g so that I avoid the fractions in my displays. So, look at the right hand side, y2x, y2t, y1 of 1 minus y2t, y21, y1x. For x less than or equal to t, you are going to get same y2 of 1 into g of x t equal to y2x, y2t, y1 of 1 minus y1 of t, y2 of 1, y2 of x. Now, look at the right hand sides. The two first terms on the right hand sides match. Look at the second terms, y2t, y21, y1x and y1t, y2 of 1, y2 of x. Now, y2 of 1 is common. y2 of 1 is common. The other two terms, y2t, y1x, y1t, y2 of x. So, when you replace x by t and t by x, these terms get interchanged. In other words, we have proved that the Green's function is a symmetric kernel. G of x t is the same as g of tx. The symmetry of the Green's function is a remarkable byproduct of our calculations, and we must take a very careful note of this. There is a very important reason for this symmetry. So, what is the cause of this symmetry in the Green's function? It is related to the fact that the 2-point boundary value problem with Dirichlet boundary condition happens to give you a self-adjoint operator. Now, there is one small comment. there is a lambda which is floating around, y double prime plus lambda rho xy equal to f of x. That was the boundary value problem with Dirichlet boundary conditions. So, in the solution there will be a lambda floating around. The Green's function is also going to depend upon lambda. So, it is more appropriate to denote the Green's function by g of x comma t comma lambda. That is one comment I would like to make. Now, let us look at this symmetry of the Green's function in other situations. Now, if you go back to basic courses on partial differential equations, you look at the theory of the Laplace's equation. So, Laplacian of u equal to f. This is called the Poisson equation. The inhomogeneous Laplace's equation is called the Poisson's equation. So, you got a domain omega in say R3 for instance, and you are solving Laplacian of u equal to f in omega. What are the side conditions? The with Dirichlet boundary condition, the u along the boundary is 0. How does this equation arise? Where does this equation arise? It arises in electrostatics, and the u happens to be the potential. And so, it says that Laplacian of u equal to f inside and the potential on the boundary is 0. So, how do you solve this equation? This solution u can be expressed as an integral. You can write u of x equal to integral of over omega g of x comma chi d chi, where d chi is d chi 1, d chi 2, d chi 3 Lebesgue measure or the usual volume measure. And so, the solution can be expressed as an integral with respect to kernel. So, u of x equal to integral over omega g of x chi f of chi d chi. And again the Green's function is symmetric. That is a theorem that you usually prove in your PDE courses. Laplace's equation, Laplacian of u equal to f, can be solved with Dirichlet boundary condition, and the solution is expressed as u of x equal to integral over omega g of x chi f of chi d chi. Again, the symmetry of the Green's function in this context is related to the self-adjointness of the boundary value problem. Exercise: consult books on PDEs for the expression for the Green's function for the ball. If you take a general domain in R3, it is usually very difficult to find a formula for the Green's function. Suppose you take an ellipsoid. Expression for the Green's function for the ellipsoid is a difficult problem. The nicest domain is a ball, and for a ball you have a nice expression for the Green's function, and consult this expression for the Green's function. It is called the Poisson kernel, and this expression will be symmetric in x and chi. Determine the Green's function for the differential equation y double prime plus lambda y equal to f on the closed interval 0, 1 with Dirichlet boundary conditions. Now, I kept using the word self-adjoint. What does self-adjointness mean? Now, let us look at this a little closely. Again, let us begin with the finite dimensional setup. Recall that if A is an n cross n real symmetric matrix, then the dot product of Ax and y is the same as the dot product of x and ay. So, the real symmetric matrix satisfies this equation: inner product Axy equal to inner product Xay for all x and y in Rn. The definition of self-adjoint operators on a Hilbert space is modeled on this. A bounded operator T from H to H, where H is a Hilbert space, is said to be self-adjoint if inner product Txy is the same as inner product x comma Ty for all xy in H. Let us examine when is a Hilbert-Schmidt operator self-adjoint. So, our nice examples of operators on a Hilbert space that we have seen are Hilbert-Schmidt operators. Why are they interesting? Because they arise from 2-point boundary value problems, and that is the main theme of this lecture series. So, it is for these operators that we must understand self-adjointness. So, when will such operators be self-adjoint? Again, we are going to assume that our density function rho x for the Sturm Liouville problem is going to be positive almost everywhere. Also, we are going to work with real valued kernels, we are going to work with real Hilbert spaces. There is no problem if you want to work with complex Hilbert spaces and complex valued kernels. At appropriate places, you have to put the complex conjugation. That is the only difference. And this modification is routine. So, let us simplify our life. Let us assume that everything is real. So, theorem 68, suppose k of xt is a continuous function on the square 0 1 cross 0 1, then the Hilbert-Schmidt operator t from L2 of 0 1 to L2 of 0 1 given by t of x equal to integral 0 to 1 k xt f of t dt is self-adjoint if and only if the kernel is symmetric. So, the self-adjointness of t is equivalent to the symmetry of the kernel. Since the Green's function is symmetric, the solution operator is going to be self-adjoint. In particular, for our boundary value problem with Dirichlet boundary conditions at 0 and 1, the solution operator is a compact self-adjoint operator. On the other hand, the Volterra operator is not a self-adjoint operator. The Volterra kernel is going to be 0 above the diagonal. Its integral 0 to x. So, if you make it an integral from 0 to 1, k of xt will be 0 above the diagonal and it is going to be 1 below the diagonal. So, it is not a symmetric kernel and so the Volterra operator is not going to be self-adjoint. It is a compact operator, all right. So, let us prove the theorem. Again, we are going to assume that the kernels are continuous and the Hilbert space is real for simplicity. Take fg in L2 of 0 1, then what is the inner product tfg? It is integral 0 to 1 k xt f of t g of x dt dx. So, first we compute tf. What is tf? K xt f of t dt, and then we are taking inner product with gx. So, one more integral comes. So, it becomes a double integral. Do it the other way around. First compute Tg. What is Tg? Ktx gx dx and pairing it with f, inner product with f. So, you have to multiply by f of t and integrate with respect to t. That is the second expression that you get on the slide. So, the condition Tf inner product with g equal to f inner product with Tg translates to the condition double integral from 0 1 cross 0 1 kxt minus ktx f of t g of x dx dt for all f and g in L2 of 0 1. So, now we are in this nice situation and this integral must be 0 for all f and for all g. In particular, I can take f to be a monomial t to the power k and g to be another monomial x to the power j, and then this should be 0. And once it is 0 for monomials, it will be 0 for polynomials in two variables. And once it is true for polynomials in two variables, it will be true for continuous functions in two variables, because every continuous function of two variables is a uniform limit of a sequence of polynomials. So, kxt minus ktx applied with phi tx should be 0 for all continuous functions phi tx. In particular, I can take the phi tx to be kxt minus ktx itself. So, what will you get? Double integral from 0 1 cross 0 1 of kxt minus ktx the whole squared dt dx is 0. Therefore, kxt must be the same as ktx and the proof is thereby completed. So, now the next thing to look at are Eigen Values. So, let us recall from linear algebra a basic result. You take a linear transformation T from Rn to Rn. Rn is a finite dimensional vector space. For a finite dimensional vector space, we have the equivalence that T is injective if and only if T is surjective. Why do I have this equivalence in a finite dimensional vector space? Because we have the rank nullity theorem. The domain is n dimensional and T is a map from Rn to Rn. So, rank of T plus nullity of T will be n, correct? So, T is injective implies the nullity is 0. So, the rank of T will be n, rank of T equal to n will imply that T is surjective. So, 1 implies 2. How do you know 2 implies 1? If T from Rn to Rn is surjective, its rank is n. So, by rank nullity theorem, its kernel or the nullity is 0 and T will be injective. So, we got the equivalence of these two things. However, in an infinite dimensional space, this equivalence fails. We do not have a rank nullity theorem in infinite dimensional Hilbert spaces. So, when you have an infinite dimensional Hilbert space and you have an operator T from H to H, which is a bounded linear operator, then we must discuss what does it mean to say that a complex number lambda is a spectral value of T or lies in the spectrum of T. So, you say that lambda lies in the spectrum of T if at least one of the following holds: T minus lambda I fails to be injective, T minus lambda I fails to be surjective. If at least one of these conditions hold, that is, if either T minus lambda I fails to be injective or if T minus lambda I fails to be surjective, we say that lambda lies in the spectrum of T. We will continue this in the next lecture.